Hello everybody, my name is David Pitones. I'm going to be solving Griffiths Problem 4.20, which says a sphere of linear dielectric material has embedded in it a uniform free charge density rho to find the potential at the center of the sphere relative to infinity, and if its radius is capital R, and the dielectric constant is epsilon sub r. So first we're going to do is we're going to draw our sphere, which has radius capital R. Note that it has a relative permittivity on the inside and a vacuum permittivity on the outside. To solve for the electric potential, we're going to have to first solve for the electric field outside and inside of the sphere. We can solve for the electric field on the outside by using Gauss's law, where on the left side of the equation we have the closed surface integral of the electric field dotted by the differential area element, and we have on the right side the charge enclosed over epsilon naught. Where in this case, since we have a free charge density rho, that means we're dealing with a volume. So we can equate the charge enclosed equal to the volume integral of the sphere times the charge density rho, right? And so now the goal for this is we're going to figure out how we can get rid of this dot product so we can solve for the left side of the equation. We know that since the sphere we're dealing with has a uniform charge distribution, this means that the charges are spread out the same every direction from the center. And so this also applies to the electric field. So the electric field is also spread out the same in every direction from the center. And we know that the electric fields that are equal distances away have the same magnitude, and even though I say different directions, this is really just the same direction, which is the radial direction. So we can break down the electric field into its magnitude times its direction, which is the r hat direction. And you could do the same for the differential area element, since the normal is just also in the radial direction. So we have dA times r hat, and so we know that r hat dot r hat is just going to go this part. So now we have our equation right here, which is, don't forget the integral parts right here. All right, so now we have this. We can pull this electric field outside of the integral, and now we can just start evaluating these integrals. So we know that the surface integral for a sphere, or the surface area of a sphere, is just equal to 4 pi r squared. And then for the charge enclosed, we know that the volume of the sphere is of radius big R. So the charge enclosed is going to be all this. And so we're going to have 4 pi over 3 times big R cubed. Don't forget that we also have rho over epsilon naught. And so the reason why I have little r right here instead of also big R is because our Gaussian surface is actually on the outside right here, and so our little r in this case is bigger than capital R. And so now what we can do right here is we can start canceling out terms. And this gives us the magnitude of the electric field, which is the following. Just double check. Yep. So this is going to be our electric field or the electric field magnitude for outside of the sphere. And since we want the electric field, and we know that the electric field is a vector, that means we have to think about the direction that the electric field is going. And since that's in the radial direction, then we can put that our electric field is equal to the following, but we also put an r hat right here, right? And so now what we're going to do is we're going to solve for the electric field on the inside. And so to solve for our electric field on the inside of the sphere, this time we're going to use this equation, which is just a small modification of Gauss's law, which on the left side, it is the closed surface integral of the electric displacement field times the differential area element, and that's going to be equal to the free charged enclosed. And so, as before, the charge enclosed doesn't change, so we know that the charged enclosed is equal to the volume charge, or the free charge volume density, and that's going to be multiplied by the volume integral of this sphere. And you might be wondering what the electric displacement field is equal to. That is actually just equal to the following, which is the absolute permittivity times the electric field. So if we substitute these two pieces into our integral, or into our equation, we should get the following. And if you notice, this is looking pretty familiar to what we had before. Just some minor modifications. And so using the similar symmetry arguments as we did in the previous part, we can pull this electric field out and we get the following integral to solve for. And we have these two integrals, which, unlike last time, this volume integral is not going to have capital R, but since we are taking the integral on the inside, that means we're going to have a radius of little r. And so to solve for this integral on the right side, we know that the volume of a sphere is just equal to 4 over 3 pi r cubed, and then this multiplied by the volume charge density. And then on the left side, we know that surface area of a sphere is just 4 pi r squared, and then we still have our electric field magnitude right here, and we still have our absolute permittivity right there. And so there's a lot of terms we can simplify. We can reduce this r cubed, cancel out this r squared, we can cancel out the 4 pi on both sides, and then we are left with the absolute permittivity times the magnitude of the electric field is equal to the volume charge density rho over 3 times r. And so if we put this absolute permittivity term onto the other side, we have the magnitude of the electric field is equal to the following. And recall that the electric field that we're looking for is a vector, not a magnitude. And so similar to last time, we know that the electric field is pointing outwards in the radial direction. And so with that, we can say that the electric field is equal to the volume charge density over 3 times the absolute permittivity times r hat. And so with this, we have both of our electric fields, and we are now able to solve for the electric potential. To solve for the electric potential, we can use the following equation, which is the electric potential is equal to the negative path integral of the electric field dotted by the differential path element. And the lower bound is going to be our reference point. Upper bound is going to be our point where we actually want to take the electric potential. And recall that in the beginning of the problem, Griffiths said that our reference point is going to be infinity, and we're taking that all the way to the center of the sphere, which is why we solved for both the electric fields so that we can use this equation properly. So we can take the electric potential from infinity to the radius of the sphere, and then we can take the electric potential from the radius all the way to the center of the sphere. So let me set both of those integrals up. The first one being that of the outside, where we're going to have the lower bound of infinity, our bound of capital R, with the electric field from the outside being the free charge density over 3 epsilon naught times r capital R cubed over r squared r hat dotted by dr r hat, which dr r hat is just equal to a differential length, a differential path element, I mean. And then our second integral is going to be going from r to 0. So we have this, and then it's going to be electric field on the inside, which is the free charge density over 3 epsilon times r hat dot dr r hat. And so now I'm going to solve the first integral right here, which isn't too bad. First, we pull out all the constant terms, and our integral just turns out to be the following. So also recall or know that since we have r hat, this dot product just cancels or turns into 1, right? We're just left with this scalar quantity. And so now we just have to take the integral of 1 over r squared, which is just equal to 1 over r, or negative 1 over r. Now we just have to evaluate this, which is just equal to minus 1 over r, capital R, minus 0, because 1 over infinity is just equal to 0. And so now that we have this, we can plug this back into, or we can bring these constants back in, and we get the following. So this capital R term reduces this r cubed right here, and then these negatives cancel out, which gives us the following. And so this is the electric potential from infinity to capital R. So now we just need the second part, which is solving for this integral right here. And so if we do that, we should get the following. This integral right here isn't too bad, actually. We're just doing the integral of r, which is just equal to r squared, evaluate from r to 0, which is just equal to negative r squared, because so r evaluated at 0 is 0, and then we have minus r squared. And so now we have this, and we are able to multiply these constants right here, and don't forget this minus sign right here. So we have negative free charge density over 3 epsilon times negative r squared, which is just going to give us the following. And this is our electric potential from r to 0. And so now we can combine both of our electric potential terms together, and that should give us our answer for electric potential going from infinity to the center of the sphere. So if we do that, we have the electric potential is equal to free charge density over 3 epsilon naught times r squared minus, or plus, free charge density over 3 epsilon r squared. And notice that we have a bunch of terms that are very similar, so we're able to take those out, or you can factor those out, better said, which gives us the following. And note, importantly, that epsilon, oops, I should write that better. Epsilon is equal to the relative permittivity times the free vacuum permittivity, which means we can replace this with the following. And that gives us, that lets us take out another term, or the epsilon term right here, or the epsilon naught term right here. And then we are just left with the following, which is this. So the electric potential is equal to the free charge density times capital R squared over 3 times the vacuum permittivity, and that's multiplied by 1 plus 1 over the relative permittivity. So that is the electric potential. My name is David Pitanes. I solved Griffiths Problem 4.20, and thank you for watching.